to go ahead and get started. We are today solving inequalities in one variable. Oh, did I start too early? I better check my computer clock. Nope, right on time. All right, so section 2.8 is the last section of chapter 2 that'll be on our next test. And we are solving inequalities in one variable. And we're going to be able to solve polynomials and rational inequalities using something brand new to us called sign charts that are very helpful when you want to know what a graph looks like. We're going to use algebraic techniques, also going to use some graphical techniques, so have your graphing calculator handy or the app that we have in Rapid Identity. And then solve real-world problems using inequalities. We won't get to that today. We've got 2 days scheduled for this section. So down here, it says, without a calculator, of course, combine the fractions and reduce your answer to lowest terms. I do want to let you know we already did this one yesterday, so we'll scrap that one. That was one of the two that I chose at the end to go over with you. So for A, this is all about, do you remember how to work with fractions? And obviously, since we covered some of these yesterday, you do. So what we would do is make everything fractions by putting our x squared over a 1, and then thinking about our LCD. And since our denominators are 1 and x, our LCD would be x. And that would mean we will need to multiply that first fraction by x on the top and the bottom to get a common denominator. And that would be x cubed over x plus 5 over x. And then, because we do have a common denominator, we go ahead and add the numerators. Now, this seems pretty basic after some of them we were looking at yesterday. But one of the things that we need to remember is we had to get the common denominator so that we could actually do the addition. Now, that seems really weird for me to be saying that because you're like, well, duh, Cedarholm. But what happens to some people is they get turned around backwards. They start working this method and then they start doing things like canceling before they've actually achieved the addition. You can't do that. With adding and subtracting, you have to have that common denominator first, and then you do the addition or subtraction. Only at the very end of the problem do you take a look at it and say, I wonder if I could simplify this. And in most cases, that's going to mean canceling. But canceling is a form of division. So the only way we can use canceling is if we can see multiplication, pure multiplication. And notice, this numerator has addition. That is not pure multiplication. If we could factor an x out of everything on the top, then we would see pure multiplication. But we can't, so that problem is done. You know, we get there and sometimes we think, there's got to be more I can do. And sometimes we can't. So for B, the only thing to be a little bit more careful with on this one is the fact that it's subtraction. But because it's not a real complicated problem, I mean, our numerator just has one term up there, shouldn't be too bad to just leave it as subtraction. The big deal is that we need that common denominator. So this first fraction, again, will need an x on the top and the bottom. And that'll be x cubed over x minus 3 over x, and that is x cubed minus 3 over x. And use the equals there for breaks in your work, you know, to show went from this step to this step to this step, and these are all equal. Again, last thing, very last thing would be, hey, can I cancel something out? But because this is subtraction, we are not seeing pure multiplication there, we cannot cancel. And then D. A little more complicated. We have more complicated denominators and actually more complicated numerator in the second fraction as well. So what we have to do just giving myself some more workspace there, is think, well, are my denominators factored? Because I can't find my LCD unless they're already factored. And they are. That's as simplified as they're going to get. And then develop a plan for that LCD, and remember everything has to be there and to its highest power. So we will need an x minus 1 to the first and a 3x minus 4 to the first. And that means this first little fraction will need a 3x minus 4 on the top and the bottom in order to give us that common denominator. And the second one we'll need an x minus 1 on the top and the bottom. Now, this is the one where, like I warned you, some people get turned around backwards. For some reason, they start this way, and then they convince themselves that they should be canceling. You just put all of that stuff there for a reason. You needed to get a common denominator before you could add and subtract. So don't start canceling. Remember, with adding and subtracting, you have to build them up first, then add and subtract, and only at the very end do you try to see, is there anything that I can cancel? So we would distribute this x through the parentheses from the right-hand side and get 3x squared minus 4x. And we would leave our denominator in that factored form. And then we would go ahead and take x plus 1 times x minus 1, noticing that that's a sum and difference pattern. So x squared minus 1 over the quantity 3x minus 4 times the quantity x minus 1. Now, we can go ahead and do the addition. We can see, hey, I've got common denominators here. Better put my little equals breaks in here. And we can go across the top and say, well, that's going to be 4x squared minus 4x minus 1 over the quantity 3x minus 4 times the quantity x minus 1. Now, if we can manage to factor 4x squared minus 4x minus 1 and somehow get it to match one of these factors in the denominator, well, then we could cancel. It's like reducing at the very end. That's exactly what we're looking for. But 4x squared minus 4x minus 1, we might want to take a second and think about that one and think whether or not that's something that we can factor. And I do want to remind you, you can use the discriminant to quickly figure out whether or not you have a trinomial that's factorable. Remember, b squared minus 4ac has to come out to be a perfect square, or it's not factorable. So in this case, our b value would be negative 4. A is 4, and C is negative 1. So this will give us 16. Following the order of operations, you do the powers first. Negative 4 times 4 is negative 4. Negative 4 times negative 1 is plus. Negative 4 times 4 is negative 16. Then times negative 1 would give us 16. That's 32. That is not a perfect square. So we're not going to be able to factor that. And we could have, just tried with a lot of different combinations here. And actually, there wouldn't even be a lot, because with 4, we don't have a lot of choices, nor do we have a lot of choices with negative 1. But if it's on a test, we'd want to be sure, hey, that's not factorable. And this would be our final answer, because we cannot factor it. So that's a really important skill, and that's why basically I went over the 3 out of 4 that I did here. We just have to remember, when you're adding and subtracting fractions, build them up so the denominators are the same, then do your addition and subtraction. Only at the very end do you try to do any canceling by factoring. All right, going to be important. I don't know if we'll get to the one where we need that today or if we'll get to it tomorrow. But we're solving inequalities in one variable, and these are inequalities. So we're using a polynomial inequality that takes the form of f of x is greater than 0, f of x is greater than or equal to 0, f of x is less than 0, f of x is less than or equal to 0, or f of x is not equal to 0, where f of x is some polynomial. So how do you show that a polynomial is greater than or equal to something? Well, that's what we're going to learn today. We're going to learn how to do all those pieces. There is a fundamental connection between inequalities and the positive or negative sign of the corresponding expression f of x. Now I need you to remember that f of x is just fancy notation for the output, for the y. So to solve f of x is greater than 0 is to find the values of x that make f of x, okay, f of x is y. My y's have to be greater than 0. Hey, that would make them positive. And that's what we're looking for. What values of x can you put in that would place your graph above the x-axis? Because that's where the y's are positive. And to solve f of x is less than 0 is to find the values of x that would make f of x, okay, logically, f of x is y is less than 0. Oh, below the x-axis, those are negatives. So we're really trying to put the visual of the graph together with the algebra today. And see, those two things, they just work in harmony. They really do. So if the expression f of x is a product, so something that's being multiplied, we can determine its sign by finding the sign of each of its factors. In order to do this, we will make a sign chart. And I was thinking about that back here, about how what I have in the red here is so close to what we're going to need to do today. Because this back piece here, really all we're going to care about today is that it will be a negative times a positive times a negative, and that result will be positive. That's what we're going to care about. Because we just need to know the output that I get. Is it positive? Is it negative? Is it 0? What's it going to do? So, to make a sign chart, basically, it just looks like a number line. And this is going to be something you have to do to solve these inequalities. We have to see this piece of work. So the first thing we'll do is we'll find the critical points. And those critical points are the same critical points we've been looking for when we've been graphing. Where's it going to be 0? You know, where's your y going to be 0? And where f of x is undefined. Well, those are our asymptotes. So we're still looking for those same things. And then number 2 says, just make a number line and put those critical values on there. Doesn't have to be a fancy number line. You don't have to make sure all your intervals are spaced. This is just a helper sign chart. That's what this is for. Pick x values between the critical values that you found in step 1. All right, so you're going to have a number line with these numbers on it, the zeros and the vertical asymptotes where it's undefined. Might be a whole, but usually not. And then we're going to figure out between those what's happening. Would we get something that's positive, negative, 0, and it shouldn't be a 0 because we already know where those are going to be. So we just want to find the sign of each individual factor. And what we'll do is we'll plug that into the factors of f of x. Not trying to see what's the exact number that would come out of here, just trying to see would it be positive or would it be negative? Because we need to know if it's positive, it's above the x-axis, and if it's negative, it's below. Record the sign on your sign chart. Then by using the signs of the factors, determine where f of x is positive or negative. That's what today is about. Finding all the critical points, coming up with this sign chart so that we can get almost a visual of what the graph is going to be doing. So we're going to start right here with example 0. It says let f of x equal the quantity x plus 3 times the quantity x minus 4 squared. Determine the real values of x that cause f of x to be 0, positive, and negative. Well, let's not worry about that right now. What we need to do is come up with a sign chart. All right. So for the sign chart, one of the first things it said to do was come up with those critical points, and those are going to be the zeros. So I'm looking at this and saying, well, this is already in factored form. Piece of cake. Negative 3 and 4. Those will be my zeros. So, like I said, I'm just going to make sure that I do keep them in order. I want the negative on the left and the positive on the right. But I don't have to put any intervals or anything between those. I just have to get a visual of what's happening with this graph. So now, I have to know where's it going to be positive and where is it going to be negative. Now, That means, oh, I hope not too much of this is in the glare spot, but it's a big problem here. That means I just need to pick something that would be to the left of -3. I'll pick -6. And I just need to determine, is it positive or is it negative? So here's what I do. I take my little -6 and I go up here and I say -6 plus 3. Oh, that's going to be negative. Put a little negative there to show that the first factor would come out negative. Then I put a -6 in the second one, but I realize, well, whatever I put in here, yeah, it'll be negative, but they're going to square it. That's going to be positive. So I'm going to end up multiplying a negative times a positive, so overall, that's going to be negative. So see how I'm doing my work kind of below my sign chart, and then I'm putting my result above? So anything to the left of -3 on my graph is actually going to go below the x-axis. Now I need something between -3 and 4, like something very easy. Oh, 0 goes there. I'll put a 0 in. So my 0 goes in. 0 plus 3, definitely going to be positive. Put a 0 in the second one, and I realize, well, again, it doesn't matter what I put in there. That's going to be squared, so that's going to be positive. So that tells me that this graph between -3 and 4 is going to be above the x-axis. Now I need something to the right of 4. I'll just try 5. So I put a 5 in. 5 plus 3, that's going to be positive. And again, I remember, no matter what I put in the second factor, it's going to be positive. Now I can answer all of their questions. So the first question they had up there was, when are we going to get some zeros? Well, we have two ways to write that. We could write it as x equals -3 and x equals 4. Or we could use number set notation, like so. Usually you'll see it in number set notation, but we're going to take that one either way for you. Now the reason I say usually it's a number set notation is because that's what we're going to use when we talk about B and C. We're going to talk about intervals. And we're using our parentheses and our square brackets and all of that good stuff again. So it would probably be better to kind of get your head wrapped around using the number set notation. All right, positives. When's it going to be positive? Oh, well, between -3 and 4. I found that. So, -3 to 4. And it's also going to be positive to the right of 4. Now, we definitely use the union notation here because it is this and this that will give you positive f of x values. And then I need to tell them the negative. Well, I had some negatives. They're right here, and they're to the left of -3. So -infinity to -3. And notice, not including -3 and 4 because those were zeros. They're not positive or negative. They're neither. All right. Well, let's put this together with everything that we know, and then we'll take a look on the graphing calculator. So, if I took x to the first and multiplied it times x squared, this would give me a degree 3 polynomial, a cubic. And it has a positive leading coefficient, so I know that it should do this and this. I know the end behavior already. Hey, that matches. It always said as you go to the left of -3, it's going to be going below the x-axis. Then, from -3 to 4, it's going to be above, but I have more than that because I know that this was a degree 2 factor. And that degree 2 tells me that that's going to be a tangent. So it's going to go some height up here, but I absolutely know it's going to come back down and hit at that 4, which I'm a little off to. I'm a little to the left there. Now, the part that I don't know is the dashed part there, and that's a local max. And remember, we can't do that without calculus. So that's the part we just have to wait for calculus for. But let's take a peek at that. So I already have that one in there for my y sub 1. Zoom 6 looks just like what we had built before the graphing calculator piece, with that dashed part of me saying, hey, I don't know how far up that's going to go. Yeah, I would have to use the graphing calculator for that. But it looks like exactly what we had, except for that max. And that's what we're looking for. We want to know all the algebra to tell us what those graphs will look like. Well, there's our first one. And it was example 0. So now we better get to example 1. Example 1. Finding where a polynomial is 0, positive, or negative. Well, that's the exact same thing we just did. Let f of x equal the quantity x plus 3 times the quantity x squared plus 1 times the quantity x minus 4 squared. Determine the real number of values of x so that it will cause f of x to be 0, positive, and negative. All right. So my sign chart. And the first part of this is actually part A, where we'd figure out the zeros. So, since it's already in factored form, that's going to be pretty nice. We got a negative 3. Oh, x squared plus 1. Well, that's not factorable. When does that equal 0? Well, I'd have to subtract 1 from both sides. And then I'd have to take the square root. Oh, that's imaginary. That's plus or minus I. So we don't get a 0 from that one, because we're talking about real-world graphing here. So that one is just going to help us with our sign chart. It's not going to give us a 0. And this last one, we can get one more 0 out of that. That'll be 4. So negative 3 and 4 will give us our zeros. They're numbers that need to go on our sign chart. And one of the things that's going to be helpful as we get further and further into these, because sometimes students lose track of, okay, which ones are my vertical asymptotes and which ones are my zeros. For your zeros, I found that students think it's incredibly helpful to mark those, just as, hey, this is a dot for these are my zeros. And then when we get to the vertical asymptotes and we put those on there, we don't mark those. So we remember that those are undefined. All right, to tell them about positive and negative, we're going to have to figure out, well, some number, doesn't matter what it is, to the left of negative 3. I'm just going to do negative 4. I'm going to go back in the factors and see, will they be positive or negative? If I put negative 4 in here, that's going to come out to be a negative. If I put negative 4 in here, it gets squared, so it's going to be positive. And if I put negative 4 in here, this will be negative, but it's going to be squared, so that's going to be positive. So I have a negative, a positive, and a positive. The result of that would be negative. Something between negative 3 and 4, why not use 0? Nice and easy. Positive, positive, positive. So again, we don't care what the numerical values are that come out of those factors. We only care, is it going to be positive or is it going to be negative? And then to the right of 4, I'll put 5 in. Positive, positive, positive. Hey, that reminds me of the last one we did. These were both positive, and then we ended up with a tangent in between. Let's take a peek. Yep, multiplicity of 2. So that's going to be a tangent. That's where the graph is going to bounce off. And we have x to the first, x squared, x squared. This is going to be a degree 5 polynomial. And it has a positive leading coefficient. Putting all that together, we can practically get the entire graph. But let's finish this up here. We want to know, when is it going to be positive? Well, we've got those again from negative 3 to 4. And 4 to infinity. And then when is it going to be negative? Well, from the negative side all the way to negative 3 on the number line. So graphically, we know the end behavior is much like any cubic actually, because this is a degree 5 and all of those odd degree polynomials behave the same. Matches up, negative and positive. And then, like I said, we know this region is supposed to be positive, but we also know that there's a multiplicity of 2 for that 0 at 4. So again, don't know how high it's going to go, but I do know it's going to bounce at 4. So let's take a look at that one. And there it is. Again, except for that local max piece in there, we have everything we need about that graph. So hopefully at this point you're saying, this is kind of a piece of cake here, Cedar Home. I don't even really need to know what the numbers are that come out of those factors. I just need to know, are they positive or negative? And then we get to this one, and we see, things just got a little tougher. 2x cubed minus 7x squared minus 10x plus 24 is greater than 0. So this time we're not going to focus on, finding parts A, B, and C. But we will, because we needed those to do our sign chart so that we could find all that good stuff. So it says we're going to find this analytically. Well, first, if they didn't give us that direction, we would try to factor this. And we would see, well, I can take an x squared out of these two. That'll give me 2x minus 7 as a factor. I could take a negative 2 out of these two. Oh, wait a second. My factor's not the same. Yeah, so because that's the only way that we know how to factor 4 terms, we'd have to throw in the towel on that factoring. And that would mean we're going to grab the graphing calculator after we list our possibles here and see what we can get. So thinking back to our rational zero theorem, had to think about it for a while. We've got a 24 in the back. We need all the factors of 24. There's lots of them, divided by all the factors of our leading coefficient, which is a 2. Just created more of them. But again, what we would do is we would grab our graphing calculator and we would see, hey, are any of these, nice ones that we can work this down synthetically with? I want to double check that I got that one punched in there right. So 2x cubed minus 7x squared minus 10x plus 24. Well, let's see if there's any nice ones in the table. 4, 0 looks good. Negative 2, 0, and 4, 0. So we'll use those two. Well, this is a cubic. So if we use those two, we can get this down to its last linear factor and we'll be able to find the other one. And you could also use the graphing calculator to find the third one, hoping that it'll come out to be some kind of fraction that won't be too awful to work with. But let's go ahead and use synthetic. 3, 2, 1, 0. It's in standard form. Again, it doesn't matter which of these you use first. I guess I just usually go after it in number line form, so I'll start with the negative. So there's the negative 2, worked out really nicely. Now we'll keep going with the 4. Also very nicely. And then let's see what we have left. Remainder constant x. Well, we need the last one of these. So we set it equal to 0. We add 3 to both sides. And we divide by 2. So that last one with the calculator, yeah, it would have shown up as 3/2, 1.5. All right, well now that I know where all those zeros are, I can make my sign chart. So I need a -2, and the next one I would come to out of 3/2 and 4 would be 3/2, and then the 4. And I need to know what's happening for each of these intervals. But let's go ahead so that you get used to doing this. Let's put the dots on the zeros. Eventually we'll get to a problem that has vertical asymptotes, so then you'll be able to tell the difference between those two. Alrighty, so if I put something to the left of -2, well, wait a second. We already know what this one looks like because we had to graph it. Now you could certainly put the negatives back in there and all that good stuff. But we did know what the graph looked like. And we're supposed to approach this one analytically. So we take a look at it and see we've got negative, positive, negative, positive. And it was a degree 3 polynomial, so it makes sense that we've got negative and positive over there. So at this point, what we still have to answer is this question up here. When is 2x cubed minus 7x squared minus 10x plus 24? When is that greater than 0? Well, that's going to be wherever we had positives. Down here. So that will be from -2 to 3/2. In union with, where's my other positive there, from 4 to infinity. Now, this one, we probably won't be putting something like this on the test because we did have to do the synthetic to find that, but you could absolutely rewrite this in its factored form. And go through and do the positive negative piece like we did. But that's kind of silly since we already had to have it in the graphing calculator anyway to take a peek at it. But we definitely want the sign chart. So if something like this shows up, at least make sure you have a sign chart. Now, it looked like that, huh? So let's just make a sketch. And we had -2. Yeah.
How did it get the first two zeros of -2 and 4?
That you had to use the graphing calculator for, since this was not going to be factorable by grouping. So you go ahead and you plug it in, and then you check your table. And we had a 0 at -2, and we had another one at 4. So those were nice ones to just start us off to get that last one. All right, so analytically, it's thinking a little bit different than the algebraic because we did have to use the graphing calculator to get us a good start there. Example 3, another solving. Solving a polynomial inequality graphically. Now here's that big skill of, wait a second, that doesn't look like the other ones. All the other ones had a 0 on one side. Yeah, so our first step here is get a 0 on one side. So we would subtract 2 and add 8x to both sides. Like so. Now, this one is flat out telling us, again, if we didn't know, we would try factoring by grouping, but I hope you can look at this and say x squared, so that could be an x minus 6. If I pull a 2 out of this, oh boy, that's not going to be factorable by grouping. That's not working. So in the end, we would grab a graphing calculator to figure these things out anyway. But before we do that, we can think, you know what, it's a cubic. So I do know a little bit about it. I know this piece. That's what I know, because it's a cubic with a positive leading coefficient. But we'd have to figure out where those zeros are. So double checking, x cubed minus 6x squared plus 8x minus 2. Got it in there. Graph. Okay, well, it doesn't look like they're nice ones, but hey, let's check the table anyway just in case. Second graph. No, no, no. Lots of negatives. Oh, super big positives and no zero anywhere in there. All right. Second trace, number 2. Let's put Blinky to work. All right, I need this one. So below it is to the left, enter. Above it is to the right, enter. Enter through guess. Yuck. All right, 0.325. Get that one on there. Second trace, number 2. Above is the left, below is the right. Don't know that one either. That's not a fraction that is just every day everybody should know. 1.461. So far it's doing this. One more. Second trace, number 2. Below it this time is to the left. Above it is to the right. 4.214, blah, blah, blah. And remember, this doesn't say perfectly 0, but the graphing calculator has 0.0000000000003. That's 0 as far as we're concerned. So 4.214. All right, just do that so I'm not writing over the top of my numbers there. So graphically, we can see where the zeros are. And now, this also changed. That says less than or equal to 0 this time. So that would be where it's negative and where it's 0. So let's see. Well, it's negative here, negative infinity up to the 0.325. But this time I'm going to have to include that because this has an equals bar. So that 0 has to be included in there. And then we have another segment here between the 1.461 and the 4.214 that's also going to be negative. And again, we have to include those zeros because this had an equals bar. So this is starting to get more specific. You know, we're just looking at, hey, is it greater than? Is it less than? Is it greater than or equal to? Less than or equal to? But we really normally, algebraically, would find the zeros, find the vertical asymptotes, make the sign chart, do all of that wonderful stuff. So this one we had to solve graphically. I wouldn't expect to see one of those on the test. I mean, we really want to see your algebra. We want to see that you're able to figure out what's going on algebraically with these. Then, example 4, solving a polynomial inequality with unusual answers. the inequalities associated with the strictly positive polynomial function. Oh, let's look. Oh yeah, look at that. Got a little parabola here, and it doesn't even get down to the x-axis. Okay, so it's f of x equals the quantity x squared plus 7 times the quantity 2x squared plus 1. All right, so it's actually a degree 4 polynomial because x squared times x squared would give us x to the 4th. So we want the solution of when is that greater than 0? Well, always, because it's above the x-axis. And it's always above, so negative infinity to infinity. Well, when is it greater than or equal to 0? Well, that's kind of silly, because, you know, we already said it's greater than 0, so it's still going to be negative infinity to infinity. When is this graph less than 0? Never. Well, like I said, we try to stick with set notation, so we're going to put the empty set, the null set, a 0 with a line, a dash through it. Not a dash, a slash. There we go. The solution set of less than or equal to 0. Never. Doesn't touch the x-axis. Doesn't go below it. So again, set notation of, hey, it's the null set. It isn't going to happen. So definitely there's not a lot of thinking with this one. There's just looking at it and saying, well, yeah, I can see what the graph is doing. So example 4 is another one that's going to be a little unusual. So let's take a peek. It says the inequalities associated with the non-negative polynomial function. So I'm looking over here and I see, oh, look at that. Looks like we get a 0 this time. We better figure out where that is. That's kind of step 1. So we've got x squared minus 3x plus 3. I don't know if I could factor that. Maybe I could find that last 0. So two numbers that multiply to 3 and add to negative 3. Well, they're not integers, so maybe that's not the one. Let me try this one. 2x minus, oh, yep, we can do that one. 2x plus 5 equals 0. Subtract the 5. Divide by 2. So this little spot right here is negative 5 halves. So if we want to know when is it greater than 0, that would mean we just have to leave negative 5 halves out, because everywhere else this graph is above the x-axis. So from negative infinity to that negative 5 halves, jump over that negative 5 halves, and go on to infinity. So that's greater than 0. Now, the next one says, well, how about greater than or equal to 0? Well, then that's everything we just had, plus we get to add in that negative 5 halves. Well, that's everything. That's negative infinity to infinity. All over the place. When is it less than 0? Well, never. Negative 5 halves is 0, and everything else is above it. So there's our empty set. And then the solution less than or equal to 0. Well, we don't have any less than, but we did have a 0. So we could either write it as x equals negative 5 halves, or, again, good idea to stick with the set notation so you're thinking about how this is number sets as you go through it. So obviously, if we can see the graph, you know, we can skip the sign chart. But like I said, most of the ones that we would have you do on the test would be the ones where you're actually doing the algebra to see what are the factors and how does all of this work together. This one, example 5, back to creating a sign chart, which is the normal piece here. We've got r of x equals, ooh, we get a rational one. So this is the one where I was talking about how students find it easier when they make their sign chart to put the dots on for the zeros and then just not put anything down for the vertical asymptotes besides the number itself. And that's what we're seeing here. So we want to figure out ones at 0, ones that's undefined, and then we want to talk about where is it positive, negative, all of that good stuff. So to get it to be 0, 2x plus 1 has to equal 0. We'd subtract 1 from both sides and divide by 2. So the number set would be negative 1/2, or x equals negative 1/2. Then we want to know where is it undefined. Oh, those are our vertical asymptotes down here. There's no canceling that's going to happen, so there's no holes. So x equals negative 3 and x equals 1. Those are vertical asymptotes. Now that I have those, I make my sign chart. So I have negative 3, negative 1/2, and 1. And my 0 is at negative 1/2. So we get that nice and labeled. And now I want to know positive and negative, what's happening here? So pick a number like negative 4, something to the left of negative 3. We'll get negative, negative, negative. So 3 negatives going to give us a negative. Something between negative 3 and negative 1/2, negative 1. So this will now be negative. A negative 1 here will still be positive. A negative 1 here will be negative. So now I have negative, positive, and negative, and it doesn't matter that one's on the top and the others are on the bottom. 2 negatives still make a positive. Between negative 1/2 and 1, 0. This will be positive. This will be positive. This will be negative. So that portion of the graph will be below the x-axis. And then something like 2. Positive, positive, positive. So our sign chart for that one, negative, positive, negative, positive. Well, now we can go back and finish up what they have here. When is r of x greater than 0? Well, that's going to be where we had positives on our sign chart. So the positives are from negative 3 to negative 1/2. In union with, because we want any place where this is going to be positive, 1 to infinity. There's our positives. And then where is r of x going to be less than 0? Well, that's where it's negative. So that's from negative infinity up to our asymptote at x equals negative 3. And then from negative 1/2 to 1. And we have our negatives in there. And do we have time to just peek at the graph? I think I've got about a minute left here. So let me graph that for you so you can see it. So we can see negative, positive, negative, positive. And a little more involved because it was hyperbolic. It was a rational expression. So we had to see that piece to get all of it. Well, this is a good place to stop. Example 6 is going to be a little bit more involved. So let me get you, there's your assignment for day 1, which is probably in a bad spot. So, sign charts for anything that doesn't say graphically or analytically. Really, really important. And if you want to make them for the analytic and graphical ones, totally okay with that. That way, you kind of get used to the idea when I have a polynomial inequality, I should really be making a sign chart for these.